Well, hey there. Wait, is that Soldier Boy I'm hearing again? Turn up the volume. Okay. Well, this gets me motivated to try another calc lesson today. We have been talking about area between curves, and excitingly enough, we are going to turn up the volume today and use some calculus to get volumes, not just of these like everyday mundane shapes, a cylinder that has a nice easy geometric formula, a rectangular box that's so mundane, and this kind of weird flattened cylinder has a good formula too. I'm talking, check out this like kind of like blimp here. And calculus actually can give you a way to calculate area, or I should say volume, of tougher to handle shapes. In terms of a joke for right now, I was just thinking of one. I was thinking I could get two pet pigs and I could name them swine and co-swine because it'd be like math and pigs. This graphic at the top appears on page 5, and we're actually not going to write a lot on this page because I want to get to the examples, finding the volume with you guys. So it says, let S be a solid of revolution. We're going to talk about this now, and on the next page we'll define that as well. That lies between x equals a and x equals b. So you have this weird shaped solid between those two x values. This is really important, if the cross-sectional area, meaning you slice this thing with a plane and you have this cross-sectional area, a of x, where a is a continuous function, so there's no problem with discontinuities, then the volume of S is given by a definite integral. The definite integral from a to b, if you integrate area, the rule is you get volume back. And here's a case where we're integrating side to side from one x value to another x value. Now remember, yesterday we were actually on our, a couple of our functions were turned on their side and we were integrating between y values. But we're back to talking about x's in this example. It's kind of crazy. This little piece of advice in italics that you see beneath it, imagine this plane just moving throughout that blimp shape. I don't think the cross-sectional area is all the same. I mean, if I cross-sectioned a nice predictable shape like this cylinder or this rectangular prism here, I would just get a bunch of cross-sections that were all the same shape. Whereas in this example, it's a moving cross-section that is constantly changing shape when you move right to left. And that's why they call calculus the mathematics of change. So in a second, we're going to get to a good method for calculating volume, and it's called the disk method. You'll see at the bottom of this page, I just printed a little proof here of if you use variables in this picture of a sphere, there's a way to prove that if you integrate the area of a sphere, which you can get from the area of the circular cross section here, you end up, when all said and done, with the formula for volume. 4/3 pi r cubed is the volume of a sphere. I actually want to move past that and try this disk method. So up at the top, you see a couple pictures of tools. And what these are, we're going to call these solids of revolution and define that here. Solids of revolution start from taking a 2D region and rotating it around a line. So I'll write the definition here. They result when a region in the plane, so I'll just say a region, is revolved, right? That's in the name, about a line. You see each of these weird tool shapes, and the bottle here has some symmetry about that line, and the line is going to be called the axis of symmetry, where you revolve the region. So we'll call that the axis of, we'll say, symmetry or revolution, since you're turning the region, the 2D region, around that line. What I'm going to try to do over the next couple of lessons is use a series of physical props and also a couple simulations on the computer to help visualize these 3D shapes, because I know it can get hard sometimes. Used commonly in engineering and manufacturing, the method we're going to use today is called the disk method. I think of a CD, like a compact disc, that has a little height to it, right? So it's a little thin cylinder here. And while a CD has a hole in the middle, we'll get to that later, this is going to be a solid circular shape like that. So a disk is a solid formed. And I'll draw you a picture of why this works. Formed by revolving a rectangle, about an axis, adjacent to one of its sides. to one of its sides. Okay, here's what I mean by that. One thing I can draw, I know some of these drawings might be a little bit rough today, and for that I apologize. I'm going to do my best. One thing I can draw is a rectangle. I can take a rectangle. I'm just going to draw an axis of revolution here. And connected to that, adjacent to one of its sides, I'm just going to draw an arbitrary rectangle, kind of hanging off of it like this. And I'll call the height of it r. I actually have a reason for calling it r and not h, because in a second, it's going to represent a radius of a circular shape. I'm going to spin. I want you to picture, and I know this is a little bit tough, but can you picture taking this line here and just twirling it round and round? So I want to spin this shape around that axis of revolution. And I'll draw my best 3D version of it right next to it now too. So I'm going to redraw the axis of revolution, put that here. And then what I end up getting is the original rectangle height mirrored top and bottom, and you're going to get this circular shape when the thing is set in motion called a disk. And the disk has radius r, the height from bottom to top is going to be r again. Now, are you buying it? It's a little bit hard to picture when I'm drawing in 2 dimensions. Take a look at this, and then we'll get to why this is important for volume. So take a look at this picture. I just have like a line here, and imagine 2 vertical lines coming down from it to generate a rectangle like I see here. When I hit revolve, watch the line spin around. You see the shape spinning around the axis of revolution. And while this computer program doesn't fill it in, you end up getting this circular shape when you started with a rectangle. Kind of cool. Back to this, let's get some rules down so we can see quickly why this is going to be useful. I see a couple pictures here of kind of, maybe the top one reminds me of a vase on its side, and the bottom one reminds me of a hyperboloid. Reminds me of those kind of like from The Simpsons, the nuclear power plant that Homer works at in Springfield. Okay, so going back up to this picture, let's say you're spinning this region around a horizontal axis of revolution. You're spinning it around the x-axis from A to B. Well, I'm claiming that what you get is this vase-like shape in 3D, if you want to darken in kind of some of the sides of it as circles. And what started as just like a rectangular cross section, a rectangular disc here, when it spins and when it goes into motion, you get this disc-like shape here, this circular cross section that's labeled on your picture. If I call the height of this r, that rectangle there, then I can also call the radius up to the top of that weird looking shape r in the picture. Now let's give this a try. Volume is going to be represented by an integral from A to B, we'll say, of the area, right? We said before on the last page, if you integrate area, the rule is you get volume. Well, what would the area be? Let's think about this shape. It's a circular cross section, so think of your formula for area of a circle. Area equals pi r squared. And I'm going to actually write r as a function of x. So instead of r, can you write capital R of x squared? And then you're integrating with respect to x as well. That's called your differential, the dx there too. So it just comes from pi r squared, area of a circle. So I'll say circle area is where we're getting that formula, right? It's nothing new. But we're going to see some problems where that radius is kind of changing. It's a low radius down here, it gets bigger and bigger and bigger. It's variable. We're going to write that radius in terms of x. And what's cool about integration is it accounts for everywhere from A to B on that picture. Even when the disk is getting smaller and larger, it's going to account for it. This one was photocopied a lot lighter, so you might want to do some darkening in with the vertical axis of revolution. Picture this shaded region from C to D spinning around a vertical line, spinning around the y-axis this time. Can you almost see this here? I know it's really faint. You get this power plant factory looking structure, not my best, but where a rectangle would have come out from here, once it's spun in motion, you get this horizontally sitting disc right in the middle of it. And you can call, again, the radius r of the disc, as well as the distance out in that 2D picture. So like a 2D and a 3D picture. Well here, since the vertical axis of symmetry is there, you're going to integrate with respect to y instead of x. So when we need it, volume still equals the integral of area, but let's go from y value to y value, from C to D, of the area in terms of y taken with respect to y. There's your big difference. So in terms of pi r squared, you're still integrating from C to D. You still have a circular disk that you're talking about, so let's use a pi, And we'll use the function for radius in terms of y with a dy. Okay, so a lot of letters, a lot of labeling. I want to put it into practice with you. This is the best part. Okay, I just ran and got a prop because I wanted to make sure I showed you this too before we leave page 6. I have an apple here, right? And you'll notice in the pictures I drew at the bottom of page 6, you only see one cross section in the middle of it, but I want you to picture a bunch of cross-sectional discs that are stacked up of different sizes. So a bunch of circular discs stacked up to create that whole entire shape. I did the same thing with this apple. I cut it up into discs. So you have these discs with a circular, if you imagine this being just like a sphere, even though an apple isn't a perfect sphere, a bunch of discs, all of different sizes and shapes. Yikes, I'm going to drop it here. But when put together, they make the full entire apple. So that's what integration does. The discs are different sizes throughout the apple, but when all added up together, you get the full volume. Okay, back to the math. Let's look at page 7 at the top here. We've got this one example where a 2D graph is given and a 3D graph is given. And I think that's good for the setup of the problem. It says, find the volume of the solid obtained by rotating about the x-axis. Okay, that's important. So your axis of revolution is the x-axis. The region under the curve, y equals square root of x. So here's y equals square root of x from 0 to 1. That's important for these problems too, that we cut off the region so it's not an infinite amount of volume. So this shaded region is what we're about to spin around the x-axis, put it in motion. You end up getting this floodlight looking picture here. It should look a little bit more 3D, and you see that this disk is drawn with a height of that disk of delta x. That's kind of the dx in the formula that we're about to put. We need to write a formula that's integrated. This is a horizontal axis of revolution, so let's use x values. Integrated from 0 to 1, we need the area in terms of x. That dx is just like that delta x, that differential, kind of what you're multiplying by there too. But just picture a bunch of disks making up that entire shape. Here is a demo for this too. So picture the shape. It's going to revolve around the x-axis, and then I'll turn it around in a second once we can see this. It's hollowed out, but picture ours being full and solid. You get this kind of, I don't know, the inside of a flashlight looking shape, or maybe a cereal bowl. Man, the apple got me hungry, and now I'm talking about cereal. Go figure. So now let's think about this cross section here. So I'm going to draw one little typical disc, and we'll call the radius of it r. Well, what is r going to equal here? Let's think. R changes, right? It's small, it gets really big, and the highest it ever gets to is 1, a radius of 1, when you're all the way at the outside of that shape. What we can do for that is, no matter what, the y value here is always the square root of x. Wherever you are on the x-axis, you'll take the square root of it to get the height of the disk. So that's what we use for the radius. We're going to call the radius square root of x, the height of every single disk that you could put in this shape here. And if area, cross-sectional area, equals, use circle area, pi r squared, let's sub in the square root of x for r. So we'll say pi times the square root of x squared, which is pretty nice since that square root and the square will cancel, and we can use pi x. So that's a big deal. We're using this for the radius, and we're squaring it when we put it into this pi r squared formula. All right, now back to our original integral. Let's plug in. We want to integrate from 0 to 1. The area formula, which we circled here, so pi x dx. And as crazy as this looks, it's going to do the trick. Pi is just a constant, so you can kind of leave it on the outside of the integral and just integrate x. And I've got pi times, here's the integral, x squared over 2, evaluated from 0 to 1. And then running out of space a tiny bit, we'll plug in 1, subtract what we get when we plug in 0. You end up with pi times a half, or pi over 2. And what should the units be? It was square units for area. Let's use units cubed for volume. And that is that. So that's our first. We cranked up the volume. We listened to Soldier Boy. We got through our first example. And I hope you'll be tuning in for the next one. See you soon.